Solutions to ECE 320 homework set number 9. The first problem, you're given the specs for MOSFET. The one we really care about is right here. The resistance is 68 milliohms when you have 5 amps flowing, that's IDS, at 10 volts VGS. In the ohmic region, the equation is as follows. IDS is K sub n. VDS is the voltage, 5 amps at 68 milliamps, 0.34 volts. Substituting, I have one equation, one unknown. Solve, K sub n should be 2.122 amps per volt squared. On problem 2, if the voltage, Vn is 0, is less than the turn-on voltage, so the MOSFET is off. In that case, I have 0 current, and the voltage drain to source is 20. If Vn is 5 volts, I'm going to guess saturated. Got a 50-50 shot. It's either saturated or ohmic. Plug it in, solve for the current. I get 4.6 amps. 4.6 amps at 10 ohms is 46 volts, which is not possible, so I guessed wrong. Instead, assume ohmic. It gives me two equations, two unknowns. The first equation is the equation in the ohmic region. I know VGS is 5, the threshold voltage is 2.9. I don't know VDS, I don't know IDS. The second equation is for the MOSFET. VDS plus I times R is 20. Two equations, two unknowns, solved, and you get 0.496 volts for VDS and 1.95 amps. The equivalent resistance then is voltage over current is 0.254 ohms. The last one is if I have 10 volts, do the same thing. Two equations, two unknowns, solve. Now VDS is 0.13 volts. IDS is 1.98 amps. And you're at 0.067 ohms. What that tells you is that the 68 milliohms is true under one condition. Change the conditions, it's no longer 68 milliohms. Here's 0.25 ohms. Down here, it's 0.06 ohms. So it depends upon the conditions, you'll get different resistance. Essentially, if you don't care about 0.2 ohms, when the MOSFET is on, the resistance is very low. 0.25, 0.06, something small. So for problem number 3, if you want to turn on and off the motor, that's the beauty of MOSFETs. It really doesn't care what this load is. It'll turn off pretty much anything. At 20 volts, whatever current you want, just when it's turned on, it's going to be roughly 0.06 ohms. For problem 4, if I want to design this using CMOS logic, I can circle the ones or zeros, your pick. I chose the zeros because I can do this in 3 groupings with zeros, takes 4 groupings with ones. If I circle the zeros, that just says that d bar, it's a d bar since I'm circling the zeros, is this logic. Or using De Morgan's theorem, I get another function B, C, and D. That's the MOSFET circuit. D bar on the low side, the N channel. If I build this circuit, if any of these are turned on, I'm pulled low. The top is the top part of the CMOS logic. If any of these are on, then I'm pulled high. So the CMOS logic looks like the following. This is the bottom side. It's B, C bar, D bar, or B bar, C bar, D. This is Y bar. If any of these are turned on, Y is pulled to ground. The top side is De Morgan's theorem. Series becomes parallel, parallel becomes series. So the blue gates, B, C bar, D bar in series, becomes B, C bar, D bar in parallel. The red gates, B bar, C bar, D in series, becomes B bar, C bar, D in parallel. And the last series becomes parallel. These 3 in parallel are now in series. That's the beauty of MOSFET, or CMOS logic. I can implement it in one shot. I don't have to use NANDs, NORs, and combination logic. One circuit will get you the answer right away.